Day to all. Today we can discuss the topic about temperature effects. For understanding the temperature effects on finite element analysis, I considered the simple structure. The structure is applied. The an axial load of 4 into 10 power 5 Newton is applied at 30 degrees Celsius to the rod as shown in figure. In that, the temperature is then reached at 60 degrees Celsius. So, the temperature is initiated from 30 degrees Celsius. After that, the temperature reached to 60 degrees Celsius. In this condition, we can calculate the following. Assemble the K and F matrices and nodal displacements, then stresses in each material, and fourth one is reaction at each material. We should calculate. In that, they are giving the data as like for aluminium, area is 1000 mm square and Young's modulus E is equal to 0.7 into 10 power 5 Newton per mm square, and alpha 1 is equal to 23 into 10 power minus 4 degrees Celsius. For steel, area 2500 mm square, Young's modulus 2 into 10 power 5 Newton per millimeter square, and then alpha 2 is equal to 12 into 10 power minus 4 bar degrees Celsius. These are all the data we have from the problem. Next, we can move to solution. In that, according to the given problem, other data are also available. Here you see the axial load of 4 into 10 power 5 Newton is available. So the 4 into 10 power 5 Newton is acted on the axis of the component. After that, we should need the delta T. What is the temperature difference? Yes, the problem initial temperature is 30 degrees Celsius and the final temperature is 60 degrees Celsius. So how much of temperature changes happened? Yes, delta T is equal to 60 degrees Celsius minus 30 degrees Celsius, which can be subtracted and get 30 degrees Celsius for temperature change value. Here alpha 1, which is the coefficient of temperature change for respective material. The element 1 is aluminum material. So the coefficient of temperature change for aluminum is 23 into 10 power minus 4 degrees bar degrees Celsius, and for steel the temperature change coefficient for steel material is 12 into 10 power minus 4 bar degrees Celsius. Likewise, we can collect the informations from the problem. Okay, after that we can move the questions. What are the findings we needed? Yes, we should find assemble the K and F matrices. First question. So how can we identify the K and F matrices? Let's see. I can move to next layer. For the reason I may, yes, in layer 2 I can write the finite element equation I should consider initially. So the finite element equation is the finite element equation for a one-dimensional problem in two nodal bar element is F1, F2, which is equal to AE by L. After that, the matrix, stiffness matrix 1, minus 1, minus 1, 1 into displacement U1, U2. Likewise, we can write the finite element equation for two nodal problems. Here in this problem we are having you see here in this problem we are having two elements, 1 and 2. The first element is aluminum, second element is steel. So we can solve the problem with element wise. So first I consider for element 1. So what happens in element there are two nodes available, node 1 and 2. How can I express? Here you see in there one, here in first element there are node 1 and node 2 available, so there are two nodes are available. So here I presented as like node 1 and node 2. After that, finite element equation for element 1 is A1 E1 divided by L1 into 1 minus 1 minus 1 1 U1 U2, this is equal to F1 F2, which is the element 1 finite element equation. After that we can substitute A1 value, E1 value in the respective formula. What is the A1 value? According to our problem, the A1 is 1000 mm square, E1 is 0.7 into 10 power 5 Newton per mm square, and L1, here you see the L1 is equal to 200 mm, L2 is equal to 300 mm. Likewise we got the data, so we can substitute the same values in the problem. Here you see, already show you, the A1 is 1000 into E1 is 0.7 into 10 power 5 divided by 200 into 1 minus 1 minus 1 1. The displacement U1 and U2 are from U1 U2, which is equal to the same equation I recall F1 F2. Likewise I got for element 1. If I simplify this terms, 1000 into 0.7 into 10 power 5, I got 3.5 into 10 power 5. The area of calculator I can collect the information. Then 1 minus 1 minus 1 1, and then U1 U2, which is equal to F1 F2. Likewise I can collect the information from the element 1 finite element equation. And then what happens with this 3.5? I can move this 3.5 into stiffness matrix. What happens? This can be written as like 1 into 10 power 5 1, which can be written as 3.5, and then minus 3.5, here also minus 3.5, and then 3.5. Then displacement U1 U2, this is equal to F1 and F2. Likewise I can write the finite element equation for element 1, which is a finite element equation for element 1. So further I can't reduce this equation, so that I can stop here itself, and then I can move to for element 2. Okay, what happens? Let's see. In element 3, I mean for element 2, sorry, for element 2, the same kind of calculation I followed in element 2. What are the nodes available? Yes, here you see in element 2 the node 2 and node 3 available, so I can write here the nodes are nodes in certain elements 2, 3 available. So finite element equation for second element is, it can be written as like A2 E2 divided by L2. After that stiffness matrix 1 minus 1 minus 1 1 into displacement U1 U2 is equal to force F. Here what is the force here? Sorry, here I made the mistake, which is for second element there is no U1 and U2, which can be started from U2 and U3, because the node is started from second and ended with 3. So U2 and U3, the force also F2 and F3. Likewise we can write the second finite element equation. After that I can substitute a2 value. What is the a2 value? Here you see, according to our a2 is equal to 1500 and Young's modulus given by 2 into 10 power 5. The same value I substituted with this equation, so that a2 is 1500 into 2 into 10 power 5 divided by L2. L2 is the length. What is the length of element 2? Which is 300 mm. So here I can utilize the 300 mm of length with this equation. So after that again terms are the same, the balance terms are same. After that u2, u3, and then which is equal to f2, f3. Likewise I can write the equation. Furthermore I can reduce this equation as like what I got. If I simplify with the calculator, I got 10 into 10 power 5. Likewise I got 10 into 10 power 5, which is equal to 1 minus 1 minus 1 1 u2 u3, which is equal to f2 f3. Likewise I got, now I can move this 10 into internal of matrix, so that which can be written as like 1 into 10 power 5, here 10 minus 10 minus 10 into 10 u2 u3, which is equal to f2 f3. Likewise I can write the equation for second element also. What is the next step? In previous we solved the element 1 equation, 1 into 10 power 5 into 3.5 minus 3.5 minus 3.5 3.5 u1 u2 is equal to f1 f2. Likewise I framed. After that, what about the next equation? Yes, the finite element 2 I got like 1 into 10 power 5, 10 into minus 10 minus 10 10 u2 u3 f2 f3. Likewise I got two equations from element 1 and element 2. What is our next step? Yes, the next step is assemble the equations. Okay, assemble the equation 1 and 2, element 1 equation and element 2 equation. We can assemble the element 1 and element 2 equations. From this, what are all the conditions we needed? Let's see. In our problem we can get what are all the 1 2 3 values. Yes, in our previous step, yes, here you see the terms 3.5 available, which can be written as like which is 1, which is 2, and also in the right which is 1 2, the first row, second row, and the first column, second column. And then I can write as like the next equation, which is here you see 10 minus 10 minus 10 10 available. So here I can get the values as like this is called a second column, this is third column. After creating finite element equation for element 1 and the finite element equation for element 2, we should assemble the equations. How? Let's see. I can explain. In finite element analysis, equation 1 for element 1 is 1 into 10 power 5, 3.5 minus 3.5 minus 3.5 3.5. After that displacement matrix and then force matrix available. Here how can we combine the equations? Let's see. The first equation we can name as like 3.5, which is the first column, and minus 3.5, which is the second column. Likewise 3.5 minus 3.5 is the first row, and minus 3.5 and 3.5 is the second row. Likewise we can name the matrix, column and rows. After that we can move to next finite element equation for row 2. Okay, I mean element 2. Here you see in element 2 also we started from the first row 10 and minus 10 available, so which can be written as like first row, and then second minus 10 available, which is the second row, and 10 minus 10 which is called as which is the I mistakenly put, it is the second row, which is the third row. Similarly these columns, the first column is called as second column and the second one is third column. Likewise we can fix. Okay, after that we can easily assemble both the equation with each other. How can we assemble? Let's see in my next slide. Okay, here you see the first column, second column available, and the first row, second row available. What happens with the next equation? Here the second column, third column available. Similarly second row and third row is available with the second finite element equation. Let's see what happens. How can we assemble those equations with each other? Yes, according to our first equation, first finite element equation and the second equation, finite element equation, we can combine the common term, which is 1 into 10 power 5, because in our second the 1 into 10 power 5 available, and in second equation also 1 into 10 power 5 available, so that I can write the common term, which is 1 into 10 power 5. After that how can I assemble the equations? Yes, what is the first row value, which is 3.5? let's see with our previous problem. The first row is 3.5, second column is started with minus 3.5. likewise I have, so I can write those things, 3.5 and minus 3.5, and the second row can be written from minus 3.5 and 3.5. let's see here. Yes, here the first row 3.5, after that minus 3.5 I can write. After that what I have with my first element equation? Yes, the second row minus 3.5 available, so that I can easily write the second row also, which is minus 3.5, and then here also 13.5. How the 13.5 came? Because in this 3.5 I have. After that, what is the next value? Let's see. In this second equation, the first column is named as second and the second column is named as 3, so that here the 10 is available, so I can call that 10 here. So 3.5 plus 10 I can write. What about the third row? Let's see in my previous slide. Okay, here you see in previous the minus 10 available, the 10, and then minus 10 available, so we can write in matrix as like here the minus 10, and then here also minus 10 and plus 10. likewise I can write. So now I merge the two matrices. Matrices means first finite element equation and the second finite element equation. The balanced term, third row is not available with the first element, so I here put in 0, and third row is not available, and the third column is also not available. So here for third column I put 0, and the third row also I put 0. After that I can move to write the displacement equation. For assembling the equation I can get u1, u2, u3, which is equal to f1, f2 and f3. I can rewrite the total equation. So this term is called as stiffness matrix, okay, so which is called as the k function, which is known as k of my problem, so which is the assembling of k. And then next the assembling of f, okay, next is assembling of f. Here we know the load factor, the f, the force is the load factor. In this problem we are having the temperature effect, so the load can be expressed with the temperature, so the load factor can be expressed as f, which is equal to E alpha into delta t. Here E is the Young's modulus, A is the area of a member, and alpha is the transfer coefficient, temperature transfer coefficient, delta t is the temperature change. After that I can write the matrix -1, 1. Likewise I can write the load factor for temperature effect. From this effect I can find the element 1 load factor. How? In element 1 there are two force term available, F1, F2. Why I write F1, F2? Here you see in this diagram, the element 1 has first node and second node, and also the element 2 has the second node and the third node. So if I consider first element means the force happening on F1, the force happening on node 2, F2. So here for considering the element 1 I can write F1 and F2. So I can present the F1 and F2 here. So this equation as the Young's modulus for first element is E1, area of first element is E1, and also alpha 1 into delta t of -1, 1. Likewise I can restructure the force equation for element 1. So if I simplify, what is the E1 according to our problem? What is E1 value? Let's see. The E1 value is 0.7 into 10 power 5 Newton per mm square, and the A1 is 1000 and alpha 1 is equal to 23 into 10 power -4 bar degree Celsius. So we can utilize the same function here, okay. So what is E1 according to our problem? E1 is equal to 0.7 into 10 power 5, 0.7 into 10 power 5 into 1000 into alpha 1. According to our problem given data, 23 into 10 power -4, and delta t. Already we found 60 degrees Celsius minus 30 degrees Celsius is the delta t. So 30 into 1 minus 1 and 1, which is the standard formula. From this we can get -1 and 1. So now we can easily find the force 1 and the force 2 from the available matrix. If I using calculator and solve this, I can get like 0.483 into 10 power 5 of -1 and 1. So which can be written as like 1 into 10 power 5. After that minus 0.483 and 0.483. Likewise I can got the equation for element 1 force equation. After that I can move to next, which is for element 2 force equation. What happens for element 2? Yes, we can see for element 2 equation, what are the components? The node element 2, the second node and the third node is available. So from the element 2 we can identify F2 and F3. Yes, we can see, okay. Yes, in this the equation finite for element element 2, the equation can be written as like F2 F3, which is equal to the general form E2 into A2 into alpha 2 delta T or minus 1 1, which is the formula. Here what is E2 A2? Let's see what is E2 A2. Yes, E2 A2 from the problem. E2 is equal to 2 into 10 power 5. A2, area of the second element is 1500 mm square, and the temperature change coefficient is 12 into 10 power minus 4. So now I can substitute those values in my element 2 force equation. So I can substitute E2 is equal to 2 into 10 power 5 into 1500 for area 2. Alpha 2, here the alpha 2, I can pick the alpha 2 value from the problem, so that 12 into 10 power minus 4, and delta T is common because the starting temperature is 30 and the ending temperature is 60. The difference between 60 and 30 is 30 degrees Celsius. So I can write here 30, and then matrix is minus 1 and 1 I can rewrite here. Okay, after that if I simplify with my calculator, I can get the values F2 and F3 and be written as like 1.08 into 10 power 5 of minus 1 1. From this I can get 1 into 10 power 5 minus 1.08 1.08. Likewise I can write the equations. Now I may get the two force equations from the problem. So now I can assemble those equations into each other. So global force vector. Next I should identify the global force vector. So global force vector, which means the three terms F1, F2 and F3. We can write what is F1, F2 in our previous. I can identify the F1 and the F2 matrix. Here you see F1, F2, which is equal to 1 into 10 power 5 minus 0.483 plus 0.483. So here I can write the F1, F2 matrix as like the common term in both the equations are 1 into 10 power 5. After that the first G minus 0.483, which is the value I got from element 1, and then in element 2 and that equation also plus 0.483 available. In that, what is the first element value, second element equation? First column value is minus 1.08. I rewrite the thing. After that the third, here 1.08 available, so that I can call that value. Here I can rewrite 1.08. From this I can get the assembling equation of a force vector as like 1 into 10 power 5 minus 0.483 minus 0.597 1.08. Likewise I can get the assembled force equations. And then what is the axial load? I didn't consider the axial load. Now I may consider only the temperature effects, so that I can add the temperature effects of element 1 and element 2. What about the next step? In our next step we should consider about the force element, where the force is acted on the second element. The force is acted, which is 4 into 10 power 5. What happens? I can collect that value and can substitute that value into our force vector. So F2 is equal to 4 into 10 power 5, because the 4 into 10 power 5 is acted on node 2. So the force 2 available, the external load, axial load is acted on node 2, so which can be expressed as like F2. Now how can I write in that equation? Let's see. So the F1 and the F2 and F3 I got from the temperature distribution, which is 1 into 10 power 5 of minus 0.483. Second value is minus 0.597, and the third row column is 1.08. Now the second element only has the axial load, so thus in the second node I can add that 4 kilonewton with this 0.597. What happens? Let's see. Now I can write the equation as like F1, F2, F3, which is equal to 1 into 10 power 5 minus 0.483 and then minus 0.597 plus the before step plus 4, which is the axial load, and then the third is 1.08. Now I consider the another term also in that equation, which is force. The axial load also I considered with the temperature effect. So this equation can be written as like 1 into 10 power 5 of minus 0.483 and then here my 3.483. If I add those things, I can get 3.483 and then 1.08. Likewise, I got the equation. Now I can substitute F1, F2, F3 values in the force equation. What I got? Yes, let's see. In the previous step, we are having the force equation. The force notations are available, so I can rewrite the thing. Here you see the equation 1 into 10 power 5, 3.5 minus 3.5, here minus 3.5, 0, 3.5 plus 10 minus 10 minus 10, 10, U1, U2, U3 available, F1, F2, F3 available with this equation. Now I can substitute F1, F2, F3 values on this equation, and we can move to identify the displacement values, which are U1, U2, U3. Let's see. How can I move and how can I get the values? Here you see I can substitute the F1 and F2, F3 values on that corresponding equation. Okay, so now what I show you the previous step equation 1 into 10 power 5 into 3.5 minus 3.5 is the second column first row element 0. After that minus 3.5, 13.5 minus 10 and then 0 minus 10, 10. Likewise I can get. After that U1, U2, U3, this is equal to 1 into 10 power 5. I substituted the values of force, identified force on that matrix, so that minus 0.483, 3.483 and 1.08. Likewise I can substitute. Now applying the boundary conditions. What is the boundary conditions in our problem? The terms boundary conditions. Yes, I can explain what are the boundary conditions we have. Yes, the boundary conditions, the initial point, first node has the 0 as the displacement, and the third node U3 is also 0, but U2 has some point load, so that which only has the displacement. So second node only has the displacement, and first node and the third node does not have any displacement, so that U2 only has the displacement. U1 and U3 are 0. Now we can substitute the values on the respective equation. Let's see here. The applying boundary condition is the next step. Applying boundary condition. What are all the boundary conditions? Boundary condition U1 is equal to 0. Already explained why U1 is equal to 0, and U2 which has the value, and U3 which is also 0. The U2 only has the value. So here I can substitute U1 and U3 is equal to 0 means I can get the equation as like 1 into 10 power 5 of 3.5 minus 3.5, 0 minus 3.5, 13.5 minus 10, and 0 minus 10 plus 10. In that I apply the boundary conditions, means U1 0, U2 has the displacement, so I rewrite the U2 here, and then U3 is also 0. Now I can write 1 into 10 power 5 minus 0.483, 3.483, 1.08. Likewise I can rewrite here in right hand side also 1 into 10 power 5 available, left hand also 1 into 10 power 5 available, so that I can remove the terms. So now I can write the equation as like 3.5 minus 3.5, 0, after that minus 3.5, 13.5 minus 10, 0 minus 10, 10, 0, U2 0, this is equal to minus 0.483, 3.483, 1.08. Likewise I can rewrite the terms. Now we should identify the next system. Here you see the first U1 term is 0 and the U3 term is also 0, so that we can neglect the third row and the third column. Third row and the third column from this matrix, and the first row and first column on the matrix, because the first element is 0 and the third element is 0. So now I got only 13.5 in this U2 only available, so I can pick those values for next step. Okay, so next what happens? Yes, let's see, I can show you what is the next step. According to our previous step, 13.5 U2 which is equal to 3.403 only I got. So from this I can get U2 is equal to 3.403 divided by 13.5. I can get 0.2521 mm. Likewise I got the value for U2 displacement with respect to temperature effect. Now the thermal stress. Next question, the third question is thermal stress happening on the elements. So thermal stress. How do I identify the thermal stress? Which is sigma is equal to E into du by dx, which is the formula. Now I can write the general form. Thermal stress is sigma is equal to E into du by dx. What happens in thermal stress? We can add other element also with this equation, which is the Young's modulus into alpha into delta T, which is the form for thermal stress identification. So for element 1, what is the thermal stress? I show you a example calculation. So that for element 1, the sigma 1, element 1, the thermal stress is called as sigma 1, so that this can be written as like E1 into, for element 1, what are the nodes available, what are the displacements available? Let's see. In this, first node available, second node available, and the third node available. But in element 1, the nodes are 1 and 2. If I consider the du by dx, means the displacement 2 minus displacement 1, which is du, the change of displacement. Here I can represent the change of displacement as like u2 minus u1, u2 minus u1 divided by the first element has the length of L1 minus E1 alpha 1 delta t. Now we know the values of E1 other things, so that I can substitute E1 as 0.7 into 10 power 5. The U2 is already we identified, U2 is 0.2521, so that 0.2521 minus, according to our boundary condition, U1 is equal to 0 divided by L1. According to our problem, L1 is 200 mm minus E. In our problem we are having 0.7 into 10 power 5 into alpha 1. Alpha 1 is equal to 23 into 10 power minus 4, the delta t into 30. If I calculate the terms with the aid of calculator, I can get sigma 1 is equal to 39.935 Newton per mm square, which is the step to identify the thermal stress at element 1. Then what about the element 2? Let's see, we calculate again for element 2, the thermal stress. What happens? The thermal stress sigma 2, isn't it? The thermal stress is sigma 2. So how can we identify the sigma 2? Sigma 2, which can be identified through E2. And what is the node? Yes, I can show you. In this, the nodes are available as like in element 2, the nodes are yes, in element 2 the nodes are 2 and 3. Here you see the elements are 2 and 3. So the change in displacement du can be written as like u3 minus u2. Let's see what happens. Here I can write the form as like u3 minus u2. Here u3 minus u2 divided by the length 2, because I consider the second element, so that here length 2 minus I needed to find the thermal stress, so that I can add the other element E2 alpha 2 into delta T, which is the formula for identification of thermal stress. Now I can substitute the values. E2 is 2 into 10 power 5 into U3, I mean U3 is 0 according to our boundary condition, and U2 is minus 0.2521. So the length 2 is 300 mm. So here I substitute 300 minus E2 is 2 into 10 power 5 into 12 into 10 power minus, what is the 10 power minus 6, which is the alpha 2 value, into delta t is 30. These values I pick from problems, and 30 is calculated. Delta t is equal to 60 degree minus 30 degree. I got this, the difference between those things, so that sigma 2 is equal to minus 240.66 Newton per mm square. If I calculated with the calculator, I got this answer for this. Next, what is the step? Yes, next I can move to find the reaction force, which is our next step. Now we found the thermal stresses on the given problem, sigma 1 and sigma 2. Now we can move to next step. The next step is reaction force. What is the formula for identifying the reaction force? Reaction force, which is equal to the R is equal to K stiffness matrix into displacement U star minus F, which is the formula for identifying the reaction force. Now I can substitute the values. The R can be written as R1, R2, R3 because we are having the 3 nodes, so that I can write as like R1, R2, R3, and then the stiffness matrix, which means 1 into 10 power 5. In previous we solved, in that other elements are 3.5 minus 3.5 0, and then here minus 3.5, and then the 13.5. Refer, in our previous steps we can find this as a stiffness matrix, minus 10, and then 0, minus 10, 10. Likewise we got, after that the displacement u1 is equal to 0, u2 is equal to 0.2521, and then u3 also 0, u3 also 0, so that the values is like 0, 0.2521 into 0. Likewise I wrote. After that the F minus F, what are the values I got? Yes, from the previous step I got the force values, 1 into 10 power minus 5 into minus 0.483, and the second element is 3 point, you refer in previous step, 403, and then 1.08. If you are having any doubt, you may reverse our video, we can find how do I write this values. Okay, after that I can simplify the total terms. From this I can get the values. Okay, in that you see how can I simplify. In this, the first row 3.5 minus 3.5, 0. If I multiply 0 means I can get 0 only. After that other values also. Now I can simplify. Okay, 1 into 10 power 5. After that the first element 3.5 into 0, here I can write 0. After that minus 3.5, here 0.251, so minus 3.5 into 0.2521. After that 0, here 0 available, so that 0 into 0, 0 plus 0, and then second minus 3.5, here 0 available. If I multiply both the things I can get 0. After that here 13.5 available, here 0.25121 available. Both the elements are in positive form, so that I can write here 0 plus 13.5 into 0.2521 minus, here you see minus 0. Likewise I can write. After that what is the next step? Yes, here 0 available. In previous step y 0 means here I got minus 10, so that here I introduce minus. Then third 0 into 0, I can write here 0. After that minus 10 available, minus 10 into 0.2521. After that what happens here? Plus 10, here plus 10 available into 0, so that plus 0 I got. Then the term minus 1 into 10 power 5 The other terms I recall 0.483 and then 3.403, 1.08. So I can rewrite those terms here. After that, the terms which can be written as like, I can further simplify 1 into 10 power 5 minus 0.8823 in second. If I add all the elements, I can get 3.403 and minus 2.521 minus 1 into 10 power 5. Other terms are minus 0.483, 3.403, 1.08. Likewise, I can frame the equation. Finally, I can solve the equation again. Okay, in this I can get what is R1, R2 and R3, which can be written as like 1 into 10 power 5. If I simplify the terms, other terms from this equation, I can write minus 0.8823. Other terms are I got minus 0.3993. Likewise, I can simplify. In that, I can write as like minus 0.3993. If I simplify the before term, I got this. After that 0, then minus 3.601. Likewise, I can simplify. So how do I got this? Yes, in previous step you see, in previous step you see minus 0.8823 available. Commonly I took 1 into 10 power 5 outside. Or that minus 0.8823 plus of minus 0.483. From this I can get minus 0.3993. Likewise, I framed this equation so that it happens. Okay, here I got minus 0.3993, 0 minus 3.0601. So the R1 can be written as like R1, which is equal to minus 0.3993 into 10 power 5 Newton, and R2 is equal to 0 Newton, and then R3 which is equal to minus 3.601 into 10 power 5 Newton. Likewise, we can write the R1, R2, R3 values. Now we should verify the R1, R2, R3 are right or not, because our force in our problem, we are having the force value is equal to 4 into 10 power 5 Newton. What about R? Yes, R is equal to R1 plus R2 plus R3. So minus 0.3993 into 10 power 5. R2 is 0 minus 0.3601 into 10 power 5. If I simplify all the terms, I can get minus 4 into 10 power 5 Newton. Here I got minus because the applied force, which is negative symbol. So verification is over because F is equal to R. So our answer is correct. Likewise, we can verify the total equation, which is the procedure for identifying the matrices F and K matrices and displacement U1, U2 and U3. Similarly, stress sigma 1, sigma 2 and finally R1 and R2, R3 values for the thermal stress problems. Okay, now you may aware about how do we identify the force values, and then how do we identify the stress values. Likewise, sigma 1 we identified, and then sigma 2 we identified. After that we can move to identify the reaction 1, reaction 2, reaction 3 values. Likewise, we can calculate with the aid of finite element analysis with the consideration of thermal effects, which is a procedure to solve the thermal effect problems in finite element analysis one-dimensional problems. If you are having any doubts, you may ask me through comment box. Thank you all.